So the next problem that I'm going to solve is a little bit more complicated because it's three-dimensional. So we have again a circuit in the shape of a circle. It's a thin ring with radius r and carries a current I. But this time we are going to find a magnetic field at a point on the axis of the ring, so at this point. So the coordinate of that point with respect to the origin in here, which is chosen as the center of the ring, is z, that's given. So we would like to express the magnetic field at that point in terms of this z, the current I, and the radius r. All right. So let me just note a few things in here. When I say axis in here, I'm talking about this axis in here, right? This is the this line in here. This is also the symmetry axis of that shape, meaning that if I rotate my shape, if I rotate my circuit around this axis by any angle I want, the circuit remains the same. So that's therefore a symmetry operation. And the reason why we are able to solve this problem is has something to do with the symmetry. Otherwise, if you ask the question of finding, for example, the magnetic field at an arbitrary point, let's say a point somewhere in here, that would be a very complicated question, right? So as a result, we don't want to deal with the complicated questions. We would like to deal with the simple ones. So as a result, I'm going to take a point on the axis, and we would like to compute the magnetic field there. There's a special reason why I'm interested in this problem, because I'm going to think of this shape. This thing is a generic dipole. So I'm going to take the limit where z goes to infinity, in which case this is the circuit is indistinguishable from a point dipole. In that case, it doesn't matter whether it is circular in shape or rectangular or some other complicated current distribution. Only the magnetic dipole moment would be important. So as a result, by solving this problem, I'm also going to solve the problem of how a dipole produce a magnetic field in space. All right, I'm going to come back this to at the very end. All right, so that's the picture again. So let's write this thing down. So first, let me show the direction of the current also in this picture. So the current flowing along that direction. So therefore, anywhere on this line, the magnetic field is along this direction. Okay, if this is the z-axis, right, the positive z-axis is along that direction. In that case, the magnetic field is always along the z-axis. So it doesn't matter whether it is at the origin or somewhere in here. Everywhere on the axis, when you compute the magnetic field, the direction is going to be the same. And so as a result, in this problem, I would like to compute the z component of the magnetic field, right? That's our whole job. So because of the symmetry in here, x and the y components of the magnetic fields are equal to 0. So as a result, we don't have to compute them, right? That's an important result, because what we are going to do is, we are going to see that when we divide this circuit into small segments, for each segment, the magnetic field produced is going to have x, y, and z components. So all three components will be non-zero in that case. But these are non-zero, but I know that their integrals will be equal to 0. So as a result, I'm just going to forget about them, right? I know that by symmetry, their integrals are equal to 0. So therefore, just don't spend time on computing them. So I'm just going to compute the z component of the magnetic field produced by a given segment, integrate it, and find the z component of the total magnetic field that we are looking for. All right, then let me erase this part, delete, and then let's start the solution. what we do is this. We just choose a small segment in here. So I'm going to shade the segment. We have the variable dl as a vector that appears in the Biot-Savart law, right? That's the point in question. Let me use a gray color for this one. So I'm going to connect the point in question with the location of the segment, the current carrying segment of the circuit. So I'm going to call the radius, that distance as little r. Let's remember that the radius is capital R, and the distance between the center and the point in question is z. So therefore, by Pythagorean theorem, r is equal to the square root of z squared plus r squared. Let's just immediately note that that distance does not depend on where you choose the segment. So that's just a constant, right? It's a constant that is expressed in terms of these given quantities. So it's independent of where I choose the segment, right? Next, let's just draw this unit vector, right? This is the r unit vector that appears in the Biot-Savart law. So we can immediately see that the angle between the length vector and the position unit vector, it is 90 degrees, right? So as a result, you can see that let me erase this magnetic field too. So that's the total magnetic field, but I would like to write the magnetic field produced by that segment only. So that's dB, right? Let's just write down the magnitude of the expression of the magnetic field in here. So that's the vector expression. So mu 0 I over 4 pi dl cross r divided by r squared. Right, that's the expression that we would like to integrate, but not so fast, right? So first we are going to investigate these. So first, we talk about the directions. So we know the directions of dl and r unit vector. Their cross product is a vector which is perpendicular to both of them. So as a result, you can see that the angle between this dB and the line connecting our point of interest to the segment is 90 degrees, because that line is parallel to r, and dB is just is expressed as the cross product of something with r. So therefore, the result is perpendicular to the r unit vector. So that angle is 90 degrees, which means I'm going to use another angle in here. So I'm going to use the white color again. So let's call that angle as theta, which means this angle is 90 minus theta, whatever it is. So therefore, that angle is also theta. All right. By using this, I can compute the z component of the magnetic field. So this is dBz, that's the magnitude of this dB multiplied with cosine theta. I need to compute the dB from this expression. So this is mu 0 I over 4 pi. The length has length dl. R unit vector is 1. Angle between them is 90 degrees. It is that angle in here is 90 degrees. So therefore, this is sine of 90 degrees divided by r squared. That's the magnitude of the magnetic field at that point. I multiply this with cosine theta, and then I get the z component. So therefore, the z component of the magnetic field is mu 0 I over 4 pi cosine theta dl divided by r squared. Right, that's the expression that I would like to integrate. Okay, so next, I don't want to spend any more time, so let me just write down an integral in here on both sides. So on the left-hand side, I'm going to get the z component of the total magnetic field. We know that the x and the y components are 0, so therefore we don't bother computing these or forming integrals for these. In here, I just noticed this. Let me erase all the unwanted things in here that might be confusing us, right? Let me erase this one as well. I don't need this anymore. I have just these expressions in here. Inside the integral, we have cosine theta in here. That appears like a variable, but that's also a constant, right? So I can even write down an expression of cosine theta in terms of the given. So that's r divided by little r. So therefore, this is r divided by the square root of z squared plus r squared, right? Capital R is a given quantity. At the beginning of the problem it is stated, so therefore it's a constant, it doesn't change. It doesn't depend on where I choose my segment. Z is also a constant similarly, so therefore cosine theta is also a constant. Which means that within that integral I have this constant in here, cosine theta is constant, r squared is constant. We have three constants, so I can take them out of the integral. And within the integral, I have just the integral of the length. And we have seen this thing, this integral of the length is just the circumference. So therefore, this is equal to 2 pi r. All right. So as a result, I just combine all of these and then write them down at the in the next page. First, let me remember these, and then I can quickly write them down. So BZ is mu 0 I divided by 4 pi cosine theta divided by r squared, and then 2 pi r. So let me check. Right? Let me cancel these 2 pi with 4 pi, so they get mu 0 I over 2. Cosine theta is capital R divided by little r. So we get r squared divided by little r cube. So I can write this thing down in terms of the given quantities. So this is z squared plus r squared. I made a mistake in here. I am going to write the 3 over 2 power to the power 3 over 2 in here. So that's the final expression. That's the expression that we are looking for. Again, let's remember this. So this is my circuit. This is my z-axis, right? This is the origin. So I compute the magnetic field at any point. So if I plot the z components of the magnetic field as a function of z, I'm going to get a curve like that. Right? You can easily see that this expression is maximum when z is equal to 0. So as a result, I'm going to have this kind of a behavior. So you can also see that when z is very large, right? Z is very large, the magnetic field goes like 1 over z cube. Right. So next, of course, I'm going to do this. So that's the solution of that problem, right? So we are done with the solution. Now I'm going to do something else. Now I'm going to actually make this dipole approximation. So I'm going to assume that this current loop is very small. So this is the case for the atomic dipoles, for example. So let me pass to this thing. So that's the case when the size of the circuit is much smaller than the point in question. So in this case, there's a circuit in here, and we have the point in here. The circuit is essentially a dipole, so it has a dipole moment. And I would like to find the magnetic field in here. So the question is, if I have a point which is at a distance z from my dipole, on the symmetry axis of the dipole. So that means if I extend the vector that the dipole points from the location of the dipole, then the point that I'm interested in, the point where I'm trying to compute the magnetic field is on that axis. So this is that distance. And what is the magnetic field produced by the dipole? All right, I can use this thing in that case. I just need to notice that is the denominator in here. This z squared is appearing next to r squared. When I'm making the approximation that r is much smaller than z, I'm essentially neglecting this within that expression r squared when it is next to z squared. Right? That's the only thing that I'm going to do. So as a result, we will say that the magnetic field is therefore approximately equal to mu 0 I divided by 2 r squared divided by z cube, right? So that's the approximate expression that we are going to write down. But I would like to express this in terms of the dipole moment. Now, this is also very simple because I know that the dipole moment, let me write it down in here. The dipole moment has it's basically the current multiplied with the area. So area is the area of the circuit, so that's pi r squared. Current is this, and the area has a vector associated with it, which is basically along the z direction. So therefore, the magnetic dipole moment is this. So z component of the magnetic dipole moment is I times pi times r squared then. Right? And interestingly, in this expression, we see I multiplied with r squared, right? So therefore, I can just join these two and write it in terms of the magnetic dipole moment. So I just need to multiply this whole expression with pi. So let's multiply it with pi. So therefore, this Bz is approximately equal to mu 0 divided by mu 0 mu z divided by 2 pi z cube. All right, that's a very nice expression actually. So as a result, I can perhaps erase everything and then rewrite it like that. So I have a certain dipole, magnetic dipole in here, perhaps an atomic dipole. All right? I have I'm drawing this axis in here. On that axis, I have a certain point in here. And I would like to compute the magnetic field in here, right? I'm going to write down the expression. But the distance between the dipole and the point in question is little r. So now I'm back with the little r notation. R is the radial distance between the source in here, source of the magnetic field, which is the dipole, and the point where I would like to compute the magnetic field, right? This r is that distance. So this is therefore given as mu 0 multiplied with the magnetic dipole moment as a vector divided by 2 pi r cube. All right, it's a colored equation. There are too many colors in here, but that's essentially the expression. So you can see that this magnetic dipole in here produces a magnetic field, but that field depends only on the magnetic dipole moment in here and the distance to that dipole, and it doesn't depend on how the current is distributed. I actually didn't show this because we have just did this calculation for a circular current loop. But now I'm just going to convince you, well, I expect you to be convinced that this actually depends only on the dipole moment, and even for a very complicated charge distribution, this result is going to be true, right? But of course, this expression depends on the position. So as a result, if you choose a point somewhere in here where that distance is, let's say, r, right? So in that case, of course, the expression will be different. So in this case, for example, the magnetic field would be I don't remember the coefficient in front, but I know that it is going to be opposite to the magnetic dipole moment. So it will be pointing exactly in the opposite direction. So the coefficient would be more or less the same. So, but I don't know what the prefactor in here is. Probably this is 4 pi r cubed, but as I said, I mean, I don't really remember this prefactor in here. But what's important in here is that we can compute the magnetic field produced by a single dipole in the dipole approximation, where the size of the dipole is very small compared to the distances that we are talking about in here. We have done this calculation only for a point on the symmetry axis of the dipole, but for other points as well, we can do this. I believe you are going to do these kind of calculations in the third year when you take the electromagnetism classes. So as a result, this is then expression then we can use, for example, when we are discussing the magnetic interactions of a magnetic dipole with some other moving charges. Especially when we are discussing the magnetism produced by a magnet, a permanent magnet, for example. In that case, just remember that we consider the permanent magnet as composed of atomic magnets. So each atomic magnet would then be described by a small dipole like that. So as a result, for these kind of situations, these kind of formulas for the magnetic fields would be important.